wait, present. Oh, oops. All right, present. Wait, can you guys see the slides or?
I can only see like half of it. You got a full screen.
Uh, right there. Can you
There
see
we are.
this?
Yep.
Yeah. Good.
All right. Okay.
Okay, so we're group one, me, Geo, Dakota, and Ollie.
Great introduction.
Okay.
Okay.
So like these are our circuits. The left one is figure 1 and the right one is figure 2. And one thing I noticed is that like they both have 4 batteries and 3 bulbs, but the one on the left is a lot dimmer than the one on the right. So yeah.
All right. So here we have a lot of questions. We have a little bit of a Q&A right here. And then we got some diagrams over here. So why do the bulbs glow? The bulbs glow because there's a power source that powers the bulbs. That'd be the batteries, obviously. And which circuit has the brighter bulbs? The parallel circuit, because the power distribution is more natural there. As you can kind of see in that diagram to the top right. And here's a really long one that I don't think we have time to read out. But yeah, that's slide 3.
I can summarize it actually pretty quickly.
Sweet, yes, please.
Okay, so for figure 1, which is this one up here, to get to L2, you have to go through L1, which means that some of the power going to L2 gets taken up by L1. So there's less power, I guess, going to L2, which means that it'll be slightly dimmer.
L2 is going to be dimmer than what?
Well, like they're all going to be like slightly dimmer
Then.
than in the parallel circuit.
Oh, I see. Okay.
All right, and then last one, circuit 3 is electrically equivalent to circuit 2 because the power output from the batteries are the same in both circuits. The amount of bulbs in the circuits don't change, so the power output has to be the same. And then for figure 2, the circuit first splits into 1/3 and 2/3, and then into 1/2 and 1/2. I don't know if that really makes sense, but what I'm trying to say is it goes from 3 arrow tails here to 2 and then to 1, because each time it's going past one of these bulbs, it's getting one arrow tail taken off.
Mhm.
And then for figure 3, it's essentially the same, but it just immediately splits into thirds instead of like how it does up here. But the amount of power needed for the circuits doesn't change, which means that they're electrically equivalent. And that's it.
That is it. Thank you, group 1. Are there questions for group 1? There better be questions, because otherwise I'm going to be really disappointed. Group 1, can you put your slides back up, please?
Oh, yeah, sorry. There.
Let's see. Yeah, go back a little bit. Okay, so forward. Oh, yeah, this one. Questions about that one? Thoughts, questions?
I have a question. How did you decide how to color code each of these?
We kind of just looked at what like we've previously done with like color coding and stuff, and then we decided that this would be like a good way to color code that.
Okay. Does anybody have suggestions about that color coding? Please. Yes.
I think like at first I thought that you guys didn't have the yellow part, but now I see that line. So I think maybe in the future just make it like a little darker yellow or something.
Yeah.
A little bit hard to see, or make sure to point it out. But yeah, I think
Oh, I
that
see. There is a yellow.
Yeah, there's a yellow dotted line around.
Okay. Totally could not see that.
Yeah.
Yes, thank you, Layla. I had the same question. This other thing, can somebody look at the top diagrams and talk to me a little bit about arrow tails and starbursts?
So for the top diagrams, for the one to the left, there's only really one wire going constantly through it. I mean, technically not one wire, but like, kind of same deal. So all the arrow tails are going to be the same. And
Violently agree with you. Yeah.
And then for the second one, the arrow tails have to split up because you divide it into 3 wires instead. And so the starburst and arrow tails are going to reflect that.
I also violently agree with you. However, that being said, if you're going to observe 4 starbursts on the one on the right and only 3 on the one on the left, what should be true about the number of arrow tails?
There should be more on the one to the right.
Right? Does that make sense?
Yep.
So, I mean, I think each diagram stands alone, like as a diagram alone, it's totally fine. But if you put the 2 diagrams together on the same slides, then people rightfully are going to ask questions like, why do you have less current going through L1 on the right when it's brighter than the L1 on the left, right? And you're like, I don't know. So just be careful when you do your arrow tailing. Thank you. You can take outside. Other feedback about, we haven't done a lot of presentation this semester, and that's on us, the teachers. There were just too many things we were trying to do at the same time, and not enough time to do it. So we haven't done a whole lot of presentations, but we have done presentations in semester 1. So feedback to group 1 about how you presented, how they presented, about their slides, about, I don't know, like in general, like now that we've done like the content, we talk a little bit about presentation skills. Yeah, Ian.
I thought all of them, they presented well with their voices and the slides were clear and easy
Mm-hmm.
to look at.
Cool. Yeah, Reed.
Yeah, I agree. I think it was a pretty good presentation. It looked good. My only advice would be to change the arrow tails for that one
Okay.
picture.
Jordan, any feedback?
Yes.
I don't know. Do you have any feedback?
No, I think they did really well. Maybe slow down a little bit next.
Slow down a little bit. Pay attention to the amount, the ratio of text to pictures on your slides, right? The last thing that someone wants is to read a slide that you're already reading. Like that's just not that fun. So either put pictures and like bullet points maybe, right? So that you can have a script. You should have a script, right? So you want to have a script, but just don't write your script on the slide, because then you're reading the slide and I'm reading the slide and they're reading the slide. And it's like, why would you want to do that? So just try to be careful. And this is, by the way, this is something that adults do all the time, right? And it just drives me bonkers. Like I watch my wife give presentations at her job and I'm like, no, that is not how you do it. Actually, she's not that bad. Her colleagues are just way worse than she is. But it's like people put too much text on their slides, right? So just cut the text, because nobody wants the text. Like text is evil. Okay. Thank you. That was really nice. Okay, good entry problem. Team number 2. Who is team 2?
I can share the slides.
Yes. Can't wait.
All right, here we are.
Mm-hmm.
Okay. Figure 4 shows the circuit we've built many times, the capacitor, and it's asking us to which capacitor plate do you think has the higher electrical pressure? We thought the bottom one, because it has more charge than the top, because the electrons flow from the negative end of the battery to the bottom plate. And as you can see on the left side of on figure 4, the flow is going around through the negative end, all through the light bulb and then into the highlighted blue on the capacitor, which is the bottom. And that makes the bottom plate have more charge than the top.
So this was the LOL diagram question, and it shows the from start to finish, start being the when you connect the circuit, and then finish, or like the end of the system is when it's done charging. And the system is isolated, which means that there are no energy interactions outside of like the objects or like the things that are inside the system.
Hi, hi. I'm sorry, my Wi-Fi's been down for a good while now.
And then E electric is the electrical potential energy of the system. EPCH is the chemical potential energy of the system, and ETH is the thermal energy of the system. And as we can see, because the energy is flowing through the circuit, there's a bit of heat released, which is shown on the right because of the two blocks, and also because it's a closed system, or an isolated system. The blocks of energy for each L in the LOL diagram add up to 5. There's a bunch of potential energy on the left one. Wait, sorry. No, wrong. Wait. No, yeah, okay. Anyways, yeah. Exactly. I don't know.
So here we have figure 4 and figure 5. We were asked to find the difference between the two, and the difference is the battery packs are reversed or flipped around as shown by the blue circles. And the capacitor charges differ because of that. So on figure 4, the capacitor charges on the bottom plate, and on figure 5, because the battery is flipped around, the capacitor charges on the top plate because the electrons are flowing from the top around through the top plate and then discharging from the bottom plate to the other side of the battery. Then here we have another circuit on figure 6 where there are 2 battery packs, and we said that the capacitor would not charge because as we see with the color coding, the whole circuit is blue, which means there's no flow of energy or no flow of electrons. And since there's no flow, there can't be any charging of the capacitor.
So this is the final question, and it was asking if the figure, like the capacitor in the figure, would be charged because of like the battery packs. And we said that the capacitor will be charged because all of the batteries are facing the same direction, which means that like all of the energy will flow in the same direction. And we said that the top capacitor plate will be charged because the negative end of the batteries are connected to the top capacitor plate, and that the top will charge and the bottom will discharge.
Thank you for listening.
Yeah.
Thank you. Questions for that group? Why do you guys choose that question? Or did you choose that question? Or did I just assign you randomly to?
I think you just assigned us the questions.
Yeah.
I did? Didn't you guys vote?
Yeah, I voted for number 1, but it's fine.
No hard feelings. Thank you, Ian, for being so understanding. Really appreciate it. Yeah, I think there were too many people signing for number 1. That was a problem. Cool. No, nice job. Right. The slides were really elegant. A little wordy, right? But I like the slide design. That was really neat. Cool. Let's see. Let's pause this. Oh, yeah. Recording. Team 3, you are up.
Okay, let me share the slides. Okay. So my group consists of Mark, Zach, Ruby, and I, and we were assigned problem 3. For problem 3, we were instructed to build a circuit that included 4 light bulbs, 3 batteries, 1 capacitor, and as many wires as we want. For the light bulbs, at least 2 bulbs needed to be parallel with each other. So this is what it looked like.
So the circuit we decided to build has 2 round bulbs running in parallel, first coming out of the battery pack, and then 2 long bulbs running in series with the capacitor between them at the end. And the circuit is powered by 3 batteries.
Here's the schematic diagram of the circuit. You can see we have the 2 batteries on the right and the 2 light bulbs parallel to each other, and the wing to the left with 2 more light bulbs and a capacitor. Here are arrow tails and the starburst for the circuit. The circuit starts with 6 arrow tails, and these split into 3 and 3 to light up the round light bulbs, which are lit up quite a bit with 6 starbursts. That charge joins back together into 6 again. We didn't put any arrow tails or starbursts in the loop to the left because at the moment captured by this schematic diagram, there's no charge flowing through this part due to the capacitor.
Okay, so for this question, we are asked to color code the circuit, and this photo is how we colored it. So the negative side, which is on top, is labeled blue, and then the bottom, which is the positive side, is labeled red. And as we know, whatever touches the red wire is red, and whatever touches the blue wire is blue.
So for problem E, we were tasked to consider the circuit in the picture above, color code it using our convention. And the problem that I ran into was that it's impossible to color code it using our convention, as our convention requires that wires have no resistance, meaning a wire's color can only be one color, and any series of connected wires that traces back to the batteries has to stay that color. However, every bit of wire in this circuit traces back to both ends. So that means either everything is yellow, which I highly doubt it's true, or each wire has a little bit of resistance. So that means you see the wire that has nothing, that has no light bulb in between it. That wire is 2 different colors now. It can be 2 different colors because of that, because it has a little bit of resistance. And if you were to build the circuit, then we believe that the first 2 light bulbs would light, but the one on the diagonal would light stronger because we've been taught that electricity takes the path of least resistance, and that's the path with the least wiring, I suppose. That's the path with the least distance that the current has to travel through a wire in order to get back to the battery. And yeah, that's it.
Thank you.
You're welcome. Leave your slides up for a sec. Questions from the audience?
I have a question. Just did you guys end up building this circuit to test that out, or?
We did build the circuit, and it did work as we had thought, with the round lit up, or the round on the diagonal lit up. The round that wasn't on the diagonal, because that's the path with the most resistance, most wires, and it's the highest Did I freeze for a minute?
Yep.
Wait, yes, did you
Yes.
say? Okay, I'm sorry. I was, so where did I freeze? Like where I was talking.
So
when did I-
you said you did build it, and it validated what your predictions were.
Okay. That's essentially all I have to say anyway. So
So here's my question to you four, right? So your solution is essentially correct, right? Short circuit wires violate our code because you can't have, if you have one wire connected to both the positive and negative end, it's definitely not yellow. It's definitely not yellow because the positive end is definitely red, and it's definitely not, so it's impossible, right? And the only way you can make it work is if you have if you admit that the wires have resistance, which means, so now that we think about that, and this is actually a question for everybody in the class to think about. If in fact the wires have resistance, that means that every inch of wire is equivalent to a small resistance. And if we continue the model that in order for there to be a flow, there needs to be a difference of color on either side of a resistance, right? That's the only way you can get a flow, is if you have a stronger pressure on one side than on the other of a resistance, be it a light bulb, be it a wire, whatever. How would we need to change the color coding to account for that? So for example, let's take the wire that comes out of the positive end of the battery and goes to the nearest resistors, the nearest light bulb, right? How would you need to change the color of that wire to reflect your newfound discovery that in fact wires do have a resistance?
I'm sorry, I'm having a hard time visualizing this.
I mean, I'm opening that to everybody, right? Anybody in the class, like, what do you think? Right now we assume that there was no resistance, and therefore the color the wire only has one color. And so it's red coming out of the battery, reaching the light bulb, and then it's blue on the other side of the battery, reaching the light bulb, right? So that works if you have a light bulb. But if you have a short circuit, it doesn't work anymore. So what we're saying is that each fraction of the wire has a small
resistance.
How would you need to change the coloring of, let's take the red wire that reaches the light bulb, right? How would you need to change the coloring of that red wire to account for the fact that now each inch of that wire has a little bit of resistance? Yeah, what do you think?
True, the longer a wire went, the closer to yellow the color would be.
Okay. Yeah, Leila, what do you think?
Yeah, I think that if we're saying for each inch there's more resistance, then like the first inch of wire would be bright red. The next one might have like the tiniest bit of orange. The next one would have a little more orange. Then the next one would be maybe orange. And the next one is orangish yellow. Like it would kind of go ombre.
Yeah, right. So you'd have to have like an entire, like, there'd be like an entire it's not exactly a rainbow, but like the wire would be multicolor, right? With a gradation. And then we'd have to decide, you still want there to be a pretty large jump. I mean, there's going to be a larger jump across the light bulb than there's going to be across each inch of the wire. So maybe you end up at the light bulb, instead of being red, you're like light red, maybe. And it's just like you're looking at shadings of red, right? From like very, very red to like a lighter red kind of thing.
I prefer to think of it as a fade, but the fade, I couldn't really replicate the fade on Google Drawings. So I just gave a simple
fine. And then think about like, and then if you have a short circuit, then you have to go all the way from red to all the way to blue across the rainbow, like red,
Mhm.
orange to yellow to blue to green, So anyway,
And in this case, that would have to go through that wire with no light bulb in between. But if it goes that far and has resistance enough to make the full rainbow, then it has too much resistance for the long bulb to have any power.
and the lawn bulb will be really, really dim, which it is.
Yeah.
Yeah. I
Because
mean,
when we built it, it was essentially non.
but you can see
glowing.
like what I want you guys to feel, right, is the power the model we use is too simple to account for short circuits. And we were able to tweak, I mean, like the solution would be complicated to compute, like what color where exactly and how much fading and how much whatever. But we are able to imagine a new model that would include some dimming, some shape, some some spectrum of red and some spectrum of blue to account for the fact that we have that, which is kind of cool, actually, if you think about it. So anyway, team 3, nicely done. Thank you. And now to finish this show, team 4. Oh, Noel with the lightning. I like it.
Can we see this all right?
Yeah, we can see.
Okay.
Okay. Hi, it's Layla.
It's Noel.
And it's Elia. And for our project, my group and I decided to solve problem 4, lightning. So we kind of just want to take you through our thought process and how we solved it.
So first, let's start off by looking back at some vocab that we've established. So an insulator is an object that does not allow for any electricity to flow through it. That means no charge flow. Some examples of this are rubber and water bottles, plastic water bottles. A resistor is an object that limits charge flow, but some charges are still able to flow through. Some examples of these are wires and light bulbs and resistors. And a conductor is not somebody that waves a baton around, but it's an object that allows for complete flow of charge. A lot of metals often can do this, like metal or aluminum foil. So we looked at graphite circuits to study charge flow. We used 3 batteries, 3 wires, and 2 light bulbs. And in the first one, we tried to see if graphite was a conductor, was able to conduct. As you can see by the fact that the light bulbs are lighting up, it can conduct electricity. But in the second one, we tried to use air to see if that could conduct energy. As you can see by the fact that the light bulbs are not lighting up, air is an insulator. But if air is an insulator, how does lightning exist?
So before we can go into that, we have to establish what is happening inside a storm cloud before there is lightning. So as the clouds gather overhead, inside those clouds, bits of ice or frozen raindrops are moving around through the air and bumping into each other. And these collisions generate an electric charge in the storm cloud. So as these charges gather, the charges separate with the positive charges on one side of the cloud and the negative charges on the other side, usually more towards the bottom. So as you can see in this diagram, all the positive charges or the red pluses are gathered on one side and the negative charges or the blue minuses are gathered towards the bottom. And as we know, opposites attract. So as these negative charges, more and more negative charges are gathering on the bottom of the cloud, on the ground below, positive charges are gathering. And since we know that charges like to take the path of least resistance or the shortest path, these charges often gather around the tallest thing in the area, such as a tree. So with the negative charges gathering in the bottom of the cloud and the positive charges building up on the ground below, the pressure becomes so enormous that air, which usually acts as an insulator, loses its insulating capacity. That pressure is so enormous that the insulating capacity of the air breaks down and allows the charges to flow through. And we see this process as lightning.
The high pressure difference in lightning corresponds with its high voltage, and this high voltage is precisely what allows it to pass through air.
So as you take a look at these lightning strikes, know this, while it may look like magic, what's really happening is we know that charges are flowing from the cloud to the ground. So this finding implies that under great enough electric pressure, anything might be able to act as a conductor. However, the pressure that builds up in a storm cloud between a storm cloud and the ground is so great. There's so much pressure that in most other cases, air probably won't be able to act as a conductor.
So how does this concept apply to us in real life? Easy, myelin. Believe it or not, our brains work in very similar ways in comparison to a circuit. Let's take myelin, a protective layer in the human body, for instance, more specifically the concept of demyelination. Here's what myelin may look like in the form of a few drawings. So what is demyelination? Demyelination is an occurrence where the myelin lining found in a human brain begins to deteriorate. This happens because the person's own immune system will attack its myelin. And this myelin is essential to survival because it acts as an insulator for your axons and nerve cells. Its purpose is to protect and to enhance the speed of electrical impulses and allows electrical activity to be faster. Demyelination can lead to many diseases and illnesses such as MS, ALS, and Parkinson's. These sometimes painful and impairing diseases have no set cure and are often fatal.
As you can see, conducting is happening everywhere in our world, from lightning in the sky to even our own bodies. Everything is on the spectrum of resistance, and because of that, some things, like air, might just need a higher voltage in order for the charge to flow through it.
And here are some links for us to cite our sources regarding demyelination, myelin, and lightning. And that's the end.
Thank you so much for listening. If you have any questions, now would be a good time to ask, or you can always email us or private chat us in the Zoom chat. Thank you.
Thank you. Great job, team 4. Questions to the team? Yes, Reed.
First of all, I liked how you used, or you had, like, this was very organized and you had like vocabulary at the beginning, which was kind of cool. But also you tested the conductivity of graphite, but when you had the two like wires connected to the tip of that pencil, were they touching or were they like separate?
I made sure that they weren't touching. I know in the photo
Okay.
it looks like they are, but there's actually like, I made sure the rubber was between them so they weren't touching.
Cool.
Yeah, if they were touching, the light bulbs would have been a lot brighter in that case.
Yeah. Great, thank you.
Any other questions?
Thank you all. These were phenomenal presentations. These were really, really, really nice. So again, thank you for that. That's really cool. Let's see, I'm sharing again the slides that I presented at the beginning. Mark was not there. So on the slide number 3, there is a link to a course survey, right? And this is really important. This is how we get feedback from you about what we do and whether it works or not. And I gathered a lot of feedback during our one-on-ones. Thank you for those. But this is sort of a way for us to sort of like take in the more formal feedback from everybody. So what I'd like you to do, it's 11:15. Class ends today at 11:50. What I'd like you to do is I'd like you to take maybe 15 minutes, right? To take the survey. That should be plenty of time, right? So it's 11:15. Let's meet back at 11:30, and then we'll just say a formal goodbye, and then we'll be on our way. Okay. So take the survey, please.
You direct messaged it to me.
I did. Ruby. Oh, why do I do that? Like still. It's really embarrassing. Okay, everyone, there was a slide. Thank you, Ruby, for letting me know.